All right, y'all. So previously in class, we were learning how to use exponential and logarithmic functions as inverses of one another. And we were using these to solve basic exponential and logarithmic equations. So as a little quick recap, when we have a log, for example, log base b of x equals y, what we saw was that I can undo this log in order to kind of understand what it means. What is the log talking about? So the way I would do it is using this little decoder ring that I've drawn here. So first, the base of the log gets raised to the power of what the log is equal to. And then that b to the y should be equal to the inside of the log. So as a result, we get b to the y equals x. The idea of logs, if you guys recall, was that a log is essentially saying whatever base we're working in, bases being the base of the exponential, the log of some value is equivalent to the power that you need to raise that base to in order to get that value, right? So b needs to be raised to this power to get x. Another example, so let's see some more examples. Previously, we saw that log base 2 of 6 was equal to x. We can use the decoder ring to say that 2 to the power of x would equal 6. And so we get 2 to the x equals 6. This was actually our original example of why logarithms are useful, because this equation here, 2 to the x equals 6, is unable to be solved. I cannot solve this equation as is. What I can do, though, is I can use a log to get log base 2 of 6 equals x, and then use a calculator to evaluate this logarithm. Today, we're actually going to talk about how I would evaluate such a logarithm with a calculator. But before we get there, let's do a couple more examples just to refresh our minds. So here I have log of 1 over 100 equals x, and I'm trying to solve for x, right? I want to know what x equals. Now, I could plug this into a calculator, but let's use some simple log rules to undo this and figure out what x is. If I have log and there's no base written, then that is implied that it is log base 10. So log base 10 of 1 over 100 equals x. I can use my decoder ring to undo it, and I would get that 10 to the x is equal to 1 over 100. Now, what I notice here is that 100 is a power of 10, right? So that looks pretty good for us so far. And one other thing is that if I have a fraction, that implies that it was a negative exponent. Because remember, if I have 1 over 100, that's the same thing as 100 to the power of negative 1. Well, what's 100 in terms of a power of 10? It's 10 squared. Right? If I have 10 squared to the negative 1, that is equivalent to 10 to the negative 2. So you can see here in my example that I've gotten that 10 to the x is equal to 10 to the negative 2. So what's x? It's got to be negative 2. That makes sense? I don't know why I'm asking y'all. You can't respond to me. I'm going to erase that just so that I have space for other problems. Let's do a couple more examples. Here I have the base is the unknown, right? So I have log base b of 8 equals 3. Once again, we can use our decoder ring to undo it. And we get that b cubed equals 8. If b cubed is 8, what would be the base? Well, I happen to know that 8 is a power of 2, and it's 2 to the third. So I know that if I do a cube root to both sides, 8, the cube root of 8 is 2, so b equals 2. Now, I promise you, not all the answers are going to be 2 here. And then let's see this last example. Here, the input of the log is unknown, and I have ln. I wanted to include this example to remind us what ln was. Now, ln is called the natural logarithm. Natural logarithm. And essentially that's just a log which has that base e. Okay, so this is the same thing as having log base e of x equals 4. If you don't remember e, look back at our classwork. So to undo this, I would get that e to the 4th is equal to x. And I'm going to actually leave that as x equals e to the power of 4. I could evaluate this with a calculator, but I'm going to leave it in this form for now, just for simplicity. So to start off things today, I wanted us to explore applying our new knowledge of using exponentials and logarithms as inverses in order to solve some modeling problems. So here I have an application problem which involves exponential growth, and we're going to use logarithms and exponentials to be able to solve it. So here it is. The conundrum of rabbits in Australia. This is one of my favorite exponential growth problems. In 1857, a small population of 24 rabbits were released in South Australia. Just 24 rabbits. The rabbits were originally released to be hunted for sport, and it was assumed that the native carnivores in Australia would help maintain the population. But the rabbits had a different idea in mind. The population of rabbits exploded exponentially, and by 1867, the population was so great that a recorded 2 million rabbits could be shot or trapped annually without really having any noticeable impact on the population. This is actually an example of something in environmental science known as an invasive species. Essentially, these rabbits were not native to Australia, right? They weren't native. They were an animal that was brought over. And what happened was the rabbits didn't actually have any natural predators. None of the carnivores that they thought were going to eat the rabbits actually really did go for the rabbits. So the rabbits were able to freely just roam the world of Australia, of South Australia, and continue to have babies. And there is a certain saying that talks about fucking like rabbits. That is not an exact, that isn't a saying for a reason. Essentially, the idea is that rabbits tend to have a lot of babies, and they have a lot of babies very frequently. And so this is why a small population of 24 rabbits in 1857 was able to explode so greatly, so that in 10 years later in 1867, they literally were recording like 2 million rabbits being shot or trapped. And they still weren't doing any good dent to the population. And this has actually been a problem for Australia since then. They even still have like way too many rabbits. All right, so let's look at the actual math. So the rabbit population can be modeled by the following exponential function. P of t equals 24 times 2 to the power of 1.87 t. Where t represents the number of years since 1857. So what does this look like? P of t is measuring the population of the rabbits. T is representing years. It's measuring years since 1857. So our first question asks, when did the population reach 1 million? All right, so let's go ahead and we can work on solving this. So the population is 1 million. So P of t equals 1 million. So I don't want red, I want black. 1 million should equal 24 times 2 to the power of 1.87 t. So to solve this, I'm trying to get t, right? I want to know what t equals. So in order to do that, I need to get t alone. The problem is that t here is in the exponent of 2. This is the exact reason that we said before that I would want to be able to use logarithms. It's to solve for the exponent on some base such that it equals a value, right? I want to solve for the exponent. So let's get going. To start off, I want to divide both sides by 24 because that coefficient there is in the way. So I'm going to get rid of it and move it over to the other side. So we have 1 million divided 24. Let's do that on a calculator real quick. All right, we get 41,667 equals 2 to the power of 1.87t. Now here's where I'm going to use logarithms to solve for the exponent. Now, if you guys remember, up here, we had seen that the way that it works is that the base of the log is the same as the base of the exponential. The power on the log is what it should end up being equal to. And the result of the power, the result of this exponential, is the input of the log. So looking at this, essentially a logarithm is going to be a base 2 here. It's going to be log base 2 because the base on my exponential is base 2. So I'm doing essentially a log base 2 to both sides. So the idea is that I input into my logarithm the result, which is this 41,667. And it should be equal to the power, because the way logs work is it says, okay, log base 2. So I'm working in base 2. A logarithm is equal to the power necessary on the base, which is necessary to get this value. So 2 to the power of 1.87t is supposed to be equal to 41,670 or 667. So now at this point, we could solve this by then just getting t alone and by dividing by 1.87 on both sides. So now we have gotten t on its own, and we see that t equals log base 2 of 41,667 divided by 1.87. Wow, what a satisfying answer, am I right, y'all? No, let's be real. We know that this sucks, right? We need to evaluate this. But we have a problem here. This log here is base 2. The base of this log is 2. And when we were using logs in our calculator, we were only able to evaluate things like log, which is the common log, so base 10. We were only able to evaluate like log of 50, or the natural log, base e of 50. So we were only able to use base 10 and base e. So how do I evaluate a log with base 2? So this problem where the base of our logarithm is not base 10 or base e introduces the need for a formula that exists called the change of base formula. If you're taking notes, which you should be, then I really recommend that you write this down. In fact, if you aren't taking notes, go ahead and pause the video right now, get some paper, get some note paper, and be writing this down. Okay, so the idea of the change of base formula is that if I have log base a of x, I can actually just split this into a fraction of logs where the inputs are x and a, right? So see how x is at the top, a is at the bottom of the base. And then what this allows me to do is actually use logarithms of any base. So you can see I've used b here to represent the variable, essentially meaning that it could be anything. So I can turn log base a of x into log base 10 of x over log base 10 of a. Or I can turn it into natural log of x over natural log of a. And all of these will give you the exact same answer. They'll all be equivalent to the same value. So I can use this to evaluate my log base 2 of, was it 41,667? That would be equivalent to, I could use log or natural log, whichever one I prefer to use. I'm going to use natural log just because I like ln. So this is equal to the ln of 41,667 over ln of 2. It's really that easy in order to evaluate any log of any base. So now all I have to do is plug ln of 41,667 into a calculator, ln of 2 into a calculator, and divide them. So let's go ahead and do that. And I got 15.35. Yeah, let's not round it to that. Let's round it to 347. So the log base 2 of 41,667 is 15.347. And we can actually double check that, right? We could say, see, what's 2 to the power of 15.347? Does it equal this? If I do that, 2 to the 15.347, let's see what that equals. So we have 2 to the power of 15.347, and I got 41,678. Lol. You can see that I got a little bit of error, and that's because of my rounding, but it's close enough, right? We'll take that. We take those. And so what we see is that when the log base 2 of 41,667 is 15.347, I divided both sides by 1.87, and I got 8.21 years. So it asked, the original question did ask us, when did the population reach 1 million? If it took 8.21 years and we're starting our timeline at 1857, all I have to do is essentially add 8 years to 1857. So when did the population reach 1 million? It happened in 1865. You'll notice that I don't actually end up needing the decimal really, because it's the year 1865 for a whole year. It doesn't matter that it's been an extra 0.21 years, still 1865. All right, so now it also asked us what was the population in 1867. So 2 years later, or 10 years later, I mean, from 1857. That's simple enough to do. We just plug 10 in for t. So we get P of t equals 24 times 2 to the power of 1.87 times 10. That 24 looks like a 9. Let me make that a 4. All right, now to evaluate this, all I have to do is just plug it all into my calculator, right? So I'm going to go ahead and do 2 to the power of that 1.87 times t, or times 10. And then we'll go ahead and multiply that by 24. And I get that the population in 1867, so the population 10 years later, is equal to 10,220,500. There is actually a decimal that I got in my answer on the calculator, but I'm not going to include the decimal. Why? Because this is measuring the rabbits, the number of rabbits, and I can't actually have 0.42 rabbits, right? Maybe I should include that rabbits in my box. And so here we have used logarithms in order to solve an exponential modeling problem. Pretty cool, yeah? What I wanted to do for this first part of the videos, before we move on to our next section, is do a little bit more practice with the change of base formula. So I wanted us to see a little bit more with the change of base. So, for example, let's say that we wanted to evaluate the following logs: log base 2 of 6 and log base 8 of 612. Well, I can easily do this using change of base. In fact, this was our original conundrum that we did, where we had, remember, 2 to the x equals 6. And so we said that log base 2 of 6 would equal x. Now we can actually evaluate that, right? I could convert this. I'm going to use common log this time. So I can convert this into log of 6 over log of 2. And we just go ahead and plug that into our calculator, and that will solve it. I'm going to leave that one open for you guys. That's going to be in our notes. Check. And for number 2, we have log base 8 of 612. I could turn that into anything, man. I could turn that into the natural log of 612 over the natural log of 8. And evaluating that is going to also be a notes check. So this is the conclusion of our first part of solving with exponentials and logarithms, mostly focused on applications, but also us focusing on change of base. In the next part of this two-part video series, we're going to talk a lot more about properties of logarithms and how we can use these different properties to simplify expressions